So I want to do the limit as x approaches -6 of f of x. And so if I'm looking at that, I want to see as x is getting closer to -6 from the right and left, what is my function, my y value getting closer to? And it looks like from the right, my y value is getting close to 5. From the left, it's also getting close to 5. Since from the right and left approach the same y value, then that means that the limit exists, and the answer there is 5. F prime of -8. And so I'm going to look at x equal -8. I'll go up to here, and I can see that's a minimum of my function, which means the derivative there is 0. The next one, I want to approach -2 from the right. So if I'm approaching -2 from the right-hand side, let's see what the y value is doing. It's going up here to positive infinity. So in other words, the limit doesn't exist, but we can say that the limit is infinite, is one way of writing how the limit doesn't exist. The next one, the integral from 2 to 4 of f of x dx. And so I can look here from 2 to 4. And this looks like just a rectangle here of height 2. So the width is 2, the height is 2, and so the answer there is 2 times 2, which is 4. And then I want the limit as x approaches 4 of f of x. And so as I come in from the left and right to 4, on the left-hand side, it's approaching the y value of 2. On the right-hand side, the function is approaching the y value of 5. Since the left and right hand do not approach the same value, then we say here the limit does not exist. Okay, this one is saying this looks like a definition of derivative here at 3, x equal 3. And so if I look here at x equal 3, that's here. And I see that the function is flat there, and so the slope is 0. So the derivative of the function f at 3 is 0. And now here, again, it's wanting the derivative. This is another formulation for the definition of derivative at 2. And I can see, again, it kind of flattens off there at 2, so the derivative there is also 0. Then it wants the limit as x approaches infinity of f of x. So I can see here as x goes out to infinity, the y values are getting closer and closer to this asymptote, and that asymptote is the y value 3. -3. And then the limit as x approaches 0 of f of x. And so as x approaches 0, I look from the right and from the left, and the function is approaching 3 from the right and 3 from the left. Since it's the same value, we say the limit exists and it approaches the y value 3. So the next one, I want to evaluate some limits or state that they don't exist. And so if I look at this one, it's wanting the limit as x approaches -3. And so one thing I've noticed is it looks like the denominator might have an issue there at -3, because if I plug in -3, I'll get 9 minus 3 minus 6, which is 0 in the denominator. So what I can do here is I can factor. This is equal to the limit as x approaches -3, and the denominator factors to x plus 3x minus 2. And as long as I keep the limit sign there, this function will have the same limit as x approaches -3 as the function 1 over x minus 2. Since I have the same denominator, or the same term in the numerator and denominator. And so what that means is that the function will have a hole, so it'll be identical to the graph of 1 over x minus 2, except it will have a hole when x equals -3. So at this point, the problem that I had in the denominator has now been fixed. So I can go ahead and plug in x equals -3 into the denominator, and I'll get 1 over -3 minus 2, which is -1/5. This one, I have the limit as x approaches 1 of that thing. Again, I can see that the denominator has an issue. If I plug in 1 directly, I'll get 0 in the denominator and 0 in the numerator. So since I have this So what I get here is I get, since we have the indeterminate form 0 over 0, we can apply L'Hopital rule. L'Hopital's rule. So since I'm getting that indeterminate form, I can go ahead and apply L'Hopital's rule. So what L'Hopital's rule, I'm going to put a little L'(H) over the equal sign. Your professor may have a different way of having you indicate that, but you should always indicate somehow that you're using L'Hopital's rule. So the limit stays, limit as x approaches 1. And then I can take the derivative of the top and the derivative of the bottom. So I get 4x cubed over 3x squared. Okay, and at this point, I have now gotten rid of the problem that I had in the denominator. So if I directly plug in x equal 1, I should be able to evaluate that limit. So since the top and bottom are both continuous, this function is continuous at 1, I can evaluate by plugging in. And once I go ahead and plug in, I don't write the limit anymore. So I'm evaluating the limit by plugging into a continuous function. So I get 4 times 1 cubed over 3 times 1 squared. And that just gives me 4 thirds. Sometimes you'll get after you do L'Hopital's rule once, you get another indeterminate form, and you may have to do it twice, but in this one, just doing L'Hopital's once worked out. Okay, so the next one says the limit as theta goes to pi over 2 of cotangent theta over cosecant theta. Okay, so the first, I just need to write this out. Cotangent is cosine over sine over 1 over sine. Okay, so I just needed to write it out with cosines and sines to see if there were any issues. I know that sine of pi over 2 is equal to 1 and cosine of pi over 2 is equal to 0. So if I just plug in the values, I can get the answer. So I think cotangent over cosecant, this thing is continuous at pi over 2. I was worried at first that we were going to have like a 0 in the denominator, but it turns out our denominators are 1, so it's actually not a problem. So if we just go ahead and plug in the pi over 2, we can get cosine of pi over 2 over sine of pi over 2 over 1 over sine of pi over 2, and we just get 0 over 1 over 1 over 1, which is just 0. So that one was continuous. So sometimes you have to watch out for that. If it's just continuous, you can just evaluate by plugging in.